What you need for interference to happen, and what we will be assuming in all our examples, is that the two sources, which here means the two slits in the barrier, are coherent, which means that either they are in phase or a constant fraction of a wavelength out of phase, so that we can always identify the places where constructive and destructive interference are happening. The other thing we assume is that there is just one wavelength, because, as we'll see, the spacing of the interference pattern depends on wavelength. So, of course, that means these days we use lasers when we want to make an interference pattern. The easiest way to make sure that the light from the two slits is coherent is to have them both illuminated by a single point source, as you saw a couple of slides back. Then we know that they are in phase, and calculations are now possible. So, we start with the fact that the two beams are in phase and have the same wavelength. So then, the type of interference will only depend on the difference between the distances travelled by the two rays. We will use the symbol delta L to mean the path length difference. If delta L is a whole number of wavelengths, then peaks coincide, and we have constructive interference. When the difference between the distances is half a wavelength, or any whole number plus half a wavelength, then we will have destructive interference. So let's start to analyse this. When we have two waves interfering on the screen, the pattern always has a bright spot in the middle, at the point P, where the two beams have travelled an equal distance. Then there must always be constructive interference. At all other points on the screen, the beams from S1 and S2 will have travelled different distances. If we look at a point Q on the screen, away from the centre, the light from S2 has travelled a shorter distance than the light from S1. Notice that the two waves at S1 and S2 are in phase, so they're just past a peak. The wave from S1 has travelled, in this case, exactly one wavelength further than the light from S2. This means the waves at that point Q are in phase, so this will be constructive interference, causing a bright spot that we call a maximum. If we look at a point R between P and Q, where the path length difference is exactly half a wavelength, the crest from one wave will coincide with the trough from the other. This means destructive interference, and we get a dark fringe. This is a minimum in the pattern. Now let's have a look at the geometry. We will look at light coming from two slits that are a distance little d apart. The light then travels to a point P on a screen. The distance from the slits to the screen is big D, and it is much larger than the spacing between the slits. If we look at the two rays R1 and R2, we see that R1 has travelled a longer distance. If you look at the close-up diagram on the bottom right, the red parts of the rays show the equal distance that they're travelling, and the green part from point B to S1 is the extra distance travelled by ray 1. That length of the green part is the path length difference, delta L. We need to find a way to get an expression for delta L in terms of the known quantities in the experiment. Now, this would be complicated, but we make the assumption that the distance to the screen, big D, is very much bigger than the slit spacing, little d. And that means we can say that R1 and R2 are parallel, and they're both at an angle theta to the central line. And then the triangle formed by S1, S2 and B that you can see on the right is a right-angled triangle. So then we can say that the path length difference, delta L, is d, little d, the slit spacing, times sine theta. Now that we know an expression for delta L, we know that we will get a maximum when delta L is a whole number of wavelengths. So that lets us know that d times sine theta equals some integer times the wavelength. So we sum that up in the equation. D sine theta equals m times lambda, and m can be 0, 1, or 2, and that is the equation for finding the maxima, which are the bright fringes. For dark fringes, the path length difference needs to be an odd number of half wavelengths. So that is, delta L, which is d sine theta, has to equal some odd number times half a wavelength. So we can sum that up most easily in the equation at the bottom. D sine theta equals m plus a half times lambda, where m again is 0, 1, 2, etc. This is the equation for the dark spots on the screen. Sometimes we want to know not just the angles of the maxima, but the distances between them. In other words, the distance y on the diagram to the mth fringe. So that will be m times the distance from one fringe to the one next to it, since they're all equally spaced. So the one in the middle is what we call the 0th fringe. That will be for sine theta is 0, and so that is straight ahead. And the ones either side of 0 we will call the first fringes, to the right and the left. Then we have m equals 2 on either side, and then m equals 3, and so on. So because y over d equals tan theta, then if we know the angle, then we can find the distance y to a particular fringe. We can use Young's double slit experiment to measure the wavelength of light if we know the slit spacing, or to find the slit spacing if we know the wavelength. But historically, Young's experiment is best known because it provided the key discriminator between waves and matter. Only waves could cancel each other out like this. Matter never could. Later, however, quantum mechanics would turn this idea on its head and blur the line between matter and waves. But that is a story for another course.